Hello, good day. Today we're going to look at a research update for my Bachelor End Project. And as you know, I'm doing my Bachelor End Project about how we can use nanomass sensors for the applicability, looking at the applicability of proteomics. So the main research question that I have for my Bachelor End Project is understanding the uncertainty in mass and time for proteomics when applied with the nanomass sensor. The main reason that we're interested in this is so that we can find in which fields of proteomics we can apply the nanomass sensor to get measurements which we otherwise could not get. Now, to do this, we of course need to take a few different perspectives. One of these perspectives is that we need to understand how the nanomass sensor interacts with different proteins. The nanomass sensor captures proteins which land on the surface, and they usually hit the surface with quite a relatively high force, which causes actually the protein to deform. To understand how this could influence the measurements when you do not know the shape of the protein on the surface, this is one of the approaches that I would like to model in my Bachelor End Project to get a better understanding of what is going on the sensors. This also requires simulating the mode frequency shifts of which the measurement is based and comparing this to the theoretical frequency shifts that you would expect when you're only calculating the frequency shift when you have a point mass. Now, we also would like to find some way to find the time uncertainty. This has not really anything to do in particular with the nanomass sensor, but has to do with a method which is commonly used, namely liquid column chromatography, which allows to separate proteins based on different properties, which is a complicated process. And this allows to separate them in time as different proteins with sometimes minor differences can actually have a big difference in the travel time to the column. And this actually allows for time separation. Now, if you have time separation and mass separation, you already have two measurements, which allows you to get a measurement in 2D space instead of 1D. And this allows you to already have a better differentiating power between proteins, which would, for example, allow you to recognize certain proteins compared to if you would only measure the mass. But of course here, especially when you're looking at single molecule measurements, it is important to know when you can actually make the argument that these are different proteins based on a measurement, or whether it could just be caused by a difference in the proteins. If in how the proteins interact with, for example, nanomass sensor or the liquid column chromatography just by sheer chance. Now, to also understand better the time uncertainty, we would have to look a little bit into how liquid column chromatography would actually work. And this also has to do with how the protein is formed. Now, all these properties also have an underlying property which has effect on all these properties or measurements, and that's namely the mass uncertainty in the proteins. Here I'm talking about how the isotopes that appear inside of the protein can actually influence the measurements that you would be taking. Now, here I combine bioinformatics and mathematics to understand the mass uncertainty of proteins. I already did around 90% of this part of the project. Now we also have a strong physics side of things when we're working with a nanomass sensor. And here already did around 70%. Then I also did around 50% of the mass uncertainty. I did already a lot of delving into how to work with consolidated physics, which is the simulator system or program that I'm using to get a better understanding of the process going on. And then we also have a sort of biophysics side of things when we're talking about the time uncertainty. Of course, this process is not inherently biological, but it is more often used in biological systems like separating proteins than anything else. So it is often related with biophysical processes. Now, first we're going to talk about mass uncertainty for proteins. This is mainly due because I already have some results on this, and that's actually quite interesting to talk about right now. Of course, I will also talk a little bit about other progresses that I've been able to make, but this one is almost fully complete, and hence I can give more insight on this side of the project. Now, due to the fact that proteins consist out of atoms, and these atoms have isotopes, there's a variance in the mass of the proteins. This variance is strongly dependent on which elements the proteins are made of. When you look at the plot in front of you, which I created with my own code, you can see that for large masses, relatively for proteins, you'll get a Gaussian distribution, even though it is consisting of delta Dirac peaks. For lower masses, this is not the case. So it is interesting, especially for smaller proteins, to get a grasp on how the probability density function of the mass of the protein is shaped like. Now, this seems somewhat trivial to compute, but it actually isn't, because the process underlying this has actually a rather big complexity when it comes to the memory requirements. The memory requirement of this process is in the order of x to the power 8, where x is the number of atoms of which the protein consists. This means that even for smaller proteins, which are made out of hundreds slash a few hundred atoms, this can actually already lead to quite some trouble when dealing with the memory requirement. I'll introduce you to the mathematics behind it and explain how I have figured out a manner to get a really good approximation of the process going on while reducing the memory requirement complexity from x to the power 8 to just x. So first, the mathematics. Imagine that each element, let's for example say carbon, has one dimension, namely the mass. Now, when you are talking about carbon, you have two stable isotopes, carbon-12 and carbon-13. These isotopes have a certain mass. These masses are not integer values, as when in the process of fission, the nucleons release some energy. This means that they're basically continuous on a continuous line. And when you are combining, for example, two different elements, like say a carbon atom and a hydrogen atom, if you want the probability density function of both of those combined, then you basically get the process mathematically described here. Now, you do not need to fully understand this process, and I'll go deeper into it later on, where I'll show you it in the most visual manner possible. But for now, you must understand that if we look at the integral, which you have on the top, you see that you have tau minus t for one probability density function. This could be your carbon for the A, and for the B, for example, your hydrogen, you have T. Now, T is a dummy variable, but it's important to notice that when you have tau minus T plus T, the sum of those two will be tau. Now, tau will be the value, will be the variable for which you'll be creating new axis. So when you look at the bottom, there's a very visual illustration that you have these two inputs and you have a new x-axis where the input value will now be tau. And you see that they basically have a sort of convolution. It's not entirely similar, but very similar. Now, I call this function the add function because it's basically adding the probability density functions when they have the same variable. And an important thing to note is that this operator is an integral, and integrals are linear, which basically means that when you have a sum of probability density functions inside of the operator, you can just take this sum out of there. Now, in the case with probability density functions, which are just simple delta direct peaks, as the arrows indicate, you can clearly see that you just have a double sum over the add operation. And as the add operation will only take in delta direct peaks and will therefore also only spew out delta direct peaks, you can see that this adding operation actually has a multiplicative effect when we're dealing with only different probability density functions. And this is the main reason why the complexity is also to the power 8. Why this exactly to the power 8 is a bit more convoluted, but you'll have to trust me there. You can always read that later in my reports, but it's mainly due to the number of isotope forms that each element have. Now, before we'll get into all this, I'll first show you a demonstration of what is actually going on. I'll show you this on the Desmos website, which is a very handy website you can use for mathematical illustrations. And I'll see you there in a bit.